Hello everyone, my name is Lucero from Geneva Lakes Astrophysics and STEAM, or GLASS Education. I'm also a sophomore at the University of Wisconsin-Madison studying physics, math, and Russian language. I'm here to discuss our educational tool aiming to use music to explain astronomical filters to students of all ages. This project is titled Musical Filters. This project was initially designed for an event funded by NASA through the Wisconsin Space Grant Consortium, WSCG, where we invited students from the Wisconsin Schools for the Deaf and Blind to learn about the progression of infrared astronomy from Sophia to James Webb. Astronomical filters are typically explained visually, like the picture on the slide. This image illustrates galaxy NGC 1512 and how different details and intensities are shown through different visible color filters along with infrared and ultraviolet. While these photos are very concise, how would you be able to learn from this if you couldn't see? The goal of musical filters is to explain the purpose of filters in an audible and tactile manner for a multisensory learning experience, which is not only more accessible to those with sensory impairments, but also proven to be more effective for learning overall. Filters are astronomical tools that allow us to isolate specific wavelengths of light that we both can and cannot see, providing us with important information about different astronomical objects. For example, infrared filters often reveal new-forming stars in nebulae that are often covered by dust and gas in the visible light photography. This is an example we use when talking to students about current astronomy infrared projects such as Sophia and James Webb, and to explain why these projects are so important in the first place. A lot of progress has been made with the Musical Filters project, and we aim to make accessible lesson plans to accompany this demonstration. We want the project to be suitable for all ages, so our lesson objectives are scalable depending on the age group or the level of the students you're working with. For example, early learners would not be expected to understand complex wave mechanics and differential equations. However, we introduce them to the idea of invisible light, or that filters separate colors of the rainbow. With intermediate learners, we would teach about the broadness of the electromagnetic spectrum and how color is related to wavelength and frequency of light. After this demonstration, intermediate students should understand the relationship that higher frequencies indicate shorter wavelengths, and they should also be able to grasp the definition of what a filter is. Meanwhile, advanced learners will be able to explain the importance of filters, examples of filters, and the mechanisms behind filters, such as whether light is absorbed, emitted, or reflected. When designing this project, we acknowledge that prerequisite knowledge is not directly correlated to age. So we want the usage of musical filters to be fluid with the needs of the class or even individual students because individualization is so pivotal to effective learning. Throughout this presentation, I will be discussing the musical filters demonstration apparatus into 4 components. I want to explain what each jargon piece means so you understand what I'm talking about when I'm referring to these components. To begin, I would like to discuss the sensor, which is the largest component that resembles the Disney Pixar lamp. It contains a solar cell that will detect light, which will then be transmitted as an electrical signal to a speaker. The speaker, which also has a built-in amplifier, plays the detected sound based on the signal based on what the solar cell detects. Then there's a light box with a small box with LED lights, with a circuit inside that flashes the LEDs at specific frequencies correlating to its color. This is the process of pulse width modulation, where the frequency at which the light is flashing is correlated to a miniature tune written for each wavelength. Finally, the filter wheel contains 5 openings with 4 filters: red, green, blue, and infrared, as well as an opening for all the light to be transmitted and detected by the sensor. The goal of our design is to be affordable and user-friendly. The housing for the sensor and the light box are 3D printed with PLA filament and, for the most part, are pretty lenient with this filament decision. There is a part of the filter wheel and a small box containing the solar cell within the sensor that should be made of a dark, matte PLA filament because it blocks infrared light. If you find that other filament can block infrared as effectively or better, you can use that as well. The circuit inside the light box contains two RGB LEDs, two 940 nanometer infrared LEDs, a Raspberry Pi Pico, a few resistors, and a breadboard. The Raspberry Pi Pico contains Python script that modulates the LEDs to specific frequencies of music which correlate to their wavelength and section of the electromagnetic spectrum. Given this, we are developing a GitHub with 3D housing files, circuit diagrams, and the Python code so everyone can have access to reproducing and creating this tool. This documentation will be available approximately early next year, 2026, on the GLASS website. So if you're looking for this documentation, please turn to our GLASS website so you can find it. Each light is programmed to flash at a specific frequency that will be detected by the sensor. The sensor will detect the frequency of the flashing LED and play a miniature tune that sounds kind of like arcade music. The speed and pitch of the tune correlate directly to the wavelength of the light it is representing, with infrared being the lowest frequency, also having the lowest tune, and blue being the highest frequency and being the highest tune. Now I will play a video that will first go through a visual representation of how filters work with a filter wheel, and then it will go into the demonstration where the filter wheel will go through and play the music according to the demonstration. First, I would like to describe what is going on in the video before I play it for users or viewers who cannot see. So the first part contains a filter wheel, red, green, blue, and clear, and then someone is turning the filter wheel and different colors are being separated where you can only see, for the most part, one color passing through the filter. However, for the clear, you can see all the colors very vividly. Then in the next part of the demonstration, someone is turning the filter wheel and then the sensor is detecting which color is flashing, and when the sensor is covered with a filter, only the light according to the code will play. I will demonstrate through the video right now. As I mentioned before, a major goal of this project was to be multisensory. We want to incorporate both visual and auditory learning so students of all sensory abilities could learn about filters. We also want the multisensory approach to create a more hands-on demonstration to simply be more engaging, because students often find that using multiple senses in a demonstration is much more engaging than only looking at pictures. We achieve these goals by using sound to represent colors, along with designing accessible instructions and lessons, so musical filters and the design of musical filters itself is very user-friendly. We firmly intend to continuously update and improve this tool. We are currently working on a haptic representation of the colors, so the demonstration can have two sensory access points for most students. We also want to improve durability for transport, for the wires and circuitry can be fragile, especially when inside a box for long car rides and transport to demonstrations, shows, etc. Lastly, we want to add supporting materials so that musical filters can be used for a larger audience. To date, we have only used this in groups of 10 students or less, and we would like to try to expand it for broader audiences. With these goals in mind, we seek to develop a reproducible, user-friendly, and engaging tool explaining filters to all students.